Hello students, in today's video, let us study about semiconductor junction. Particularly, we will look into a PN junction. So as you know, a PN junction is formed when a p-type and an n-type materials are merged together. As you know, the energy levels of p-type material and an n-type material are different. In a p-type material, we have the valence band and the conduction band, and the Fermi level is closer to the valence band, whereas in an n-type material, the Fermi level is closer to the conduction band. So as you all know, when materials form junctions, the Fermi level will be equalized. Fermi level has to be brought to the same level. All other energy bands and levels are adjusted with regard to that. So when we form a PN junction diode, as indicated in this figure, there is a change in energy bands. As you can see, the Fermi level is made to the same level, is equalized across the junction, and other energy levels are adjusted as shown in the figure. So in the P region, we have to keep the Fermi level closer to the valence band, and in the N region, we have to keep the Fermi level closer to the conduction band. So as a result, in between at the junction region, we have a transition of valence band and the conduction band like a sloping hill. Now, if we look into this setup, now let us have an understanding about the number of electrons moving from the P region to the N region as well as from the N region to the P region. So as you know, electrons in the conduction band are able to conduct, are able to move across the junction, and how many number of electrons will be there in this conduction band of a p-type material? So in the classes of carrier concentration in semiconductors, we have derived equation for number of electrons. So in the case of a p-type material, the number of electrons is actually proportional to exponential minus delta E by kT. Delta E is this energy gap. So I can write NP is proportional to exponential minus ECP minus EF divided by kT. So this minus side is common to both. So that much number of minority carriers, electrons will be there in the conduction band of a p-type material. In the case of an n-type material, that delta E is very small. It is ECN minus EF, which is very small. So in the case of an n-type material, I can write the number of electrons in the conduction band is actually proportional to exponential minus of ECN, N stands for n-type, minus EF divided by kT. So since the ECN minus EF is very small, number of electrons will be larger. Now we know in a steady condition, the electrons from the P region can move across this junction. So it can have a downhill motion to this junction into the N region. Similarly, the electrons from the N region will slowly move uphill to enter into P region. So thus the electrons in the N region and P region can move across the junction as allowed by the energy bands. And let us calculate what will be the current due to the motion of these electrons. So since on the P side we have this much number of electrons, NP number of electrons, which is proportional to exponential minus ECP minus EF by kT, I can write that current Ig, that is the current existing from the motion of electrons from the P region into the N region, that will also be proportional to that factor, that is exponential minus ECP minus EF by kT, because current is proportional to number of electrons, and as a result the electrons that are moving from the P region into the N region will be proportional to that factor. Similarly, there is a current due to the motion of electrons from the N region to the P region, which we call as IR, and let us calculate that current. So as we know, in the case of electrons moving from P to N, Ig is simply proportional to Np. But in the case of electron moving from N side to P side, they have to overcome a potential barrier, or they have to move uphill along increasing energy. So not all electrons are possible to overcome that energy, and only electrons, a fraction of electrons within a range of exponential minus delta E by kT will be able to overcome that, will be able to move across that junction. So where this delta E is the barrier. How much is that barrier? That barrier is ECP minus ECN, right? Here delta E is equal to ECP minus ECN. So even though there are this much number of electrons available in the conduction band, only a fraction of exponential minus delta E by kT of these electrons will be able to move across the junction. So when we write the equation for IR, which is due to the electron motion from N side to the P side, that will be proportional to exponential minus of ECN minus EF by kT, which is the NP factor, multiplied by exponential minus delta E by kT, which is exponential minus ECP minus ECN by kT. So what will be this factor? If you multiply this ECN term will get cancelled. The remaining term will be exponential minus of ECP minus EF by kT. So this will be the current from N side to the P side due to the motion of electrons. So as you can see, electrons are moving from the P side to the N side and from the N side to the P side. But you know, in a steady state, there is no charge carrier motion across a junction, no current existing across a junction. So we can say in a steady state condition, Ig equal to IR. So you can see that this IR factor and the Ig factor are same, one and same. They are both proportional to same factors, and at a steady state there is no net current existing across the junction. Current is 0. Now let us see what will happen if we apply a V voltage. So if we apply a voltage to a PN junction diode, that will modify the energy levels of the PN junction. So here you can see it is a PN junction and we are applying a forward bias to this junction. So as you can see, it will shift the energy levels or reduce this energy barrier by an amount EV. So earlier it was ECP minus ECN. Now it will be further reduced by an amount. Delta E will be reduced by an amount of EV, where V is the applied voltage. So as a result, we can see Ig will not have any change because Ig is exponential minus ECP minus EF by kT. These factors does not change, but what changes is this delta E factor. That means ECP minus EF. So Ig, which is the electron motion from the P side to the N side, will be same because you know they are not facing any barrier at all when they move right. They are already moving downhill, and even if the hill size is less, they will be moving in the same rate. But in the case of motion of electrons from the N side to the P side, they are moving uphill, and reducing this height will have a greater effect on that. So if the size of that barrier is reduced by the EV, then we know Ig will be unchanged, but IR will be changed to Ig into exponential EV by kT. So you can simply prove it by substituting another factor of minus EV here. Then you can cancel out terms and you can prove that it will be, the new IR will be exponential minus ECP minus EF by KT, which is IG, multiplied by exponential EV by KT. So do as an assignment, simply add a term plus EV here and you can see, subtract a term EV here because the barrier height is now reduced, and you can see that our new equation for IR will be IG into exponential EV by KT. So if we apply a voltage, we have seen that the current from the P side to the N side is same. The current from the N side to the P side will be changed like this. So what will be the net current across the junction? We know the net current IE will be IR minus IG. So this is the current from N side to the P side and this is the current from P side to the N side. So it will be IG into exponential EV by KT minus 1. So this is the equation for current across a PN junction, a semiconductor junction. So this is the much famous diode equation. You have studied this equation, ID equal to I0 into exponential EV by KT minus 1, right? So this is the diode equation, which is IV equal to I0 into exponential EV by KT minus 1. Here I0 is the reverse saturation current, also called dark current, and if we apply V voltage across the junction, IV will be the current produced. So what will happen if we are applying negative voltage to this cell, to this junction? So if we are applying negative voltages, I will be equal to I0 into exponential minus EV by KT minus 1. So as you can see, if this voltage increase faster, this exponential term will fall faster because this is exponential minus term. So it will be approximately minus I0 beyond a particular voltage. So this is already something you are familiar with because you know the current is reverse saturation current when we are applying negative voltages for a PN junction, semiconductor junction. So let us see the energy band diagram when we apply a reverse voltage to a semiconductor junction. So here we have applied a negative voltage to the P side and a positive voltage to the N side. So the difference in energy will be, the barrier will increase by EV. Earlier when we are applying a forward voltage, barrier decreases by ECP minus ECN is the earlier height. It will decrease by EV. Here it will increase by plus EV. So now we know no more electrons can move across this junction, and we can see that the current will be varying like in this equation in the case of a reverse bias semiconductor junction. So as you know, if you plot this curve of a current through a semiconductor junction, if you plot this equation, the graph is simply the VI characteristic. So as you know, if you plot current versus voltage, voltage versus current along the voltage along the x-axis and current along the y-axis, this curve IV equal to I0 into exponential EV by KT minus 1 simply represents the characteristics of a PN junction. So this is all about the semiconductor junction. We have learned about the formation of this PN junction, how the energies differ, and we learned about the current from both the directions, and from that we derived the current equation, which is the diode equation, and we also used the concepts of forward bias and reverse bias and explained it based on the motion of current. So I hope this portion is clear for you. Thank you.